Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today we are going to discuss about a module, Heisenberg's uncertainty principle, under the paper Quantum Mechanics 1. So students, let us see what all we are going to learn in this module. First of all, we'll know what is the statement of Heisenberg's uncertainty principle. Secondly, we'll learn through a measurement experiment how the process of trying to determine the position using a precise value of momentum not only gives an inaccurate position determination, but at the same time introduces the uncertainty into the momentum measurement itself. Thirdly, we learn through another measurement experiment that even if the position is known precisely at the beginning of the experiment, the process of measuring momentum not only gives uncertainty in the momentum measurement, but at the same time introduces uncertainty in its position also. Fourthly, know through a few typical examples the implications and consequences of using the uncertainty principle. Then we learn the complementary principle as given by Bohr. Finally, in this module, which is in continuation of the preceding one, we'll get introduced to the concepts such as Heisenberg's uncertainty principle and the complementary principle enunciated by Bohr. In the preceding module, while discussing the wave packets in space and time, we found that there were fundamental limitations placed by the wave packet picture on the accuracy with which both the position and the momentum of a particle can be specified. In fact, from the theory of Fourier transform, it can be shown quite generally that if we have a wave packet in space that has a spread delta x, then the Fourier transform must be a non-vanishing number over a range of width delta k, where k is the wave number of the harmonic waves, with delta k is greater than or equal to 1 by delta x, and delta x is the spread in the position of the wave packet. In other words, the spread in momenta delta p of the de Broglie waves contributing to wave packet satisfies an inequality delta p delta x is greater than equal to h cross, where h cross is h by 2 pi and h is the Planck's constant. Similar inequality between energy and time also holds when we consider a wave packet in time constructed from the superposition of a spectrum of harmonic waves in frequencies or angular frequencies. That means which has different angular frequencies or frequencies. This is essential content of the uncertainty principle, which we shall be studying in the present module. The underlying idea that the basic properties of matter, such as momentum and position, do not exist in quantum theory in a precisely defined form, constitute a far-reaching change that led Bohr to enunciate in terms of what he called the complementary principle. This will be illustrated through the example of a double-slit experiment in the present module. So let us first of all state what the uncertainty principle says. So, statement of principle. In simple terms, it says that if the x-coordinate of the position of a quantum mechanical particle is known to an accuracy delta x, where delta x is the uncertainty in the determination of the position, then the x component of the corresponding momentum variable cannot be determined to an accuracy better than px is approximately equal to h by delta x. In other words, one cannot determine precisely and simultaneously the values of both the members of a particular pair of physical variables known as canonically conjugate to each other, which define a given atomic system. The x or y or z component of the position coordinate of a particle and the corresponding components of momentum L, x or y or z, or a component of angular momentum and its angular coordinate phi in the xy plane, the energy E of a particle and the time t at which it is measured, are typical examples of canonically conjugate variables. Quantitatively, we can express the Heisenberg's uncertainty principle in three separate forms, depending upon which canonically conjugate pair of variables we are choosing. So if we choose the position and the momentum, then the Heisenberg's uncertainty principle can be stated as delta x, delta px is greater than or equal to h cross, where h cross is equal to h by 2 pi and h is the Planck's constant. Similarly, if we are using the angular momentum and the angular coordinate, then the Heisenberg's uncertainty principle can be stated as delta Lz, delta phi is greater than or equal to h cross, where h cross is the same as defined earlier. And in terms of the energy and time coordinate system, we can again define the Heisenberg's uncertainty principle as delta E, delta t is greater than or equal to h cross. Measurement experiment on position. Now we'll try and see that how the uncertainty principle affects the measurement on the position of a particle. So for that, let us look at an experiment which can tell us how this is happening. So let us illustrate the uncertainty principle through a measurement experiment to show how quantum effects intervene to prevent measurements of unlimited precision. That means that it is impossible to actually determine the exact position of a particle. Suppose we wish to determine the position of a small object with precision using a microscope. The limit to the accuracy delta x with which a position can be determined is given by its resolving power, where the resolving power is given by delta x is equal to lambda by sine alpha, where lambda is the wavelength of the radiation that enters the objective lens and alpha is the half angle subtended at the position of the particle P by the objective lens. The students can see this in the figure also to get a clear picture of what we are discussing. Now suppose one quanta of light, quanta q, is scattered by the particle. Now what happens over here is that whenever a light quanta strikes the particle, it imparts a certain momentum to the particle. And this momentum that is imparted to the particle is of the order of h by lambda, where lambda is the wavelength of the radiation that is hitting the particle. So, as lens has a finite aperture, the direction in which photon is scattered into the lens is not precisely known. However, using the fact that the momentum associated with the wavelength lambda is h by lambda, as we had just discussed, the uncertainty in the x component of the momentum delta px is of the order of h by lambda sine alpha, where alpha is the half angle subtended at the aperture of the microscope. Since in the process of scattering of the light quantum, the object P itself recoils, which means that the moment the light quanta hits the particle and imparts a momentum which is of the order of h by lambda or h by lambda sine alpha, then this momentum gives a recoil to the particle, and as a result, the particle starts moving or gets disturbed. So, the x component of the recoil momentum is also uncertain to the same extent. That means that delta px is of the order of h by lambda sine alpha is equal to h by delta x, where h by delta x is the uncertainty in the recoil momentum of the particle, showing in the process of determining the very position. Momentum itself is made uncertain, given by the uncertainty relation. Delta x delta px is approximately equal to or of the order of h cross, where h cross is h by 2 pi and h is the Planck's constant. So here what is happening is that because of the inherent uncertainty in determining the momentum of the scattered particle, that is delta px, we are introducing an uncertainty in determining the exact position of the particle, that is delta x, where delta x would always be greater than or equal to lambda, that is the wavelength of the incident light. In this manner, one can see that while we are wanting to exactly determine the position of the particle, but the main impediment or the hurdle that is coming in the process is due to the very process that we are adopting, which means that whenever we try to probe the position of a particle, we will need some external stimuli which will exactly determine where the particle is located. This external stimuli, like in the case of the present experiment, happens to be light, and because the light will also interact with the particle, being quantum in nature and having a quanta of energy which acts like a particle. So what is happening is that it will give some kind of a recoil to the particle, and this recoil to the particle actually causes the hurdle in exactly determining the position of the particle, which is expressed by the uncertainty relation, that is delta x delta px is of the order of h cross. Momentum determination experiment. Now let us look at the determination of momentum exactly for a small particle, and for that again let us perform an experiment, and through this experiment we would be able to see how the experiment itself causes an uncertainty in the measurement of the momentum. So like in the last experiment, we reached the uncertainty principle by trying to measure the exact position of the particle. In this experiment, we will again try and reach the uncertainty principle, but through an attempt to measure the exact momentum of the particle. So, let us consider a different experiment in which the position is accurately known initially and the momentum is measured. Consider the method of measuring momentum by determining the velocity by means of Doppler shift of the light radiated by the particle. Here we have an atom which is in excited state at a time when it is at rest. Now suppose it emits radiation of frequency mu. So what will happen? If the atom is moving towards the observer, its observed frequency will change because of the Doppler shift, and that change in the observed frequency can be seen from the formula mu prime is equivalent to mu within brackets 1 plus mu by c, or mu by c is equal to mu prime minus mu upon mu, where mu prime is the observed frequency of the atom and mu is the actual frequency of the emitted radiation. The uncertainty in the velocity depends on the accuracy with which this observed frequency mu prime is measured, subject to the relation delta mu prime is approximately equal to or of the order of 1 by tau, where tau is a measure of the uncertainty in the instant at which photon is emitted. This makes position uncertain by delta x is approximately equal to h mu prime tau by mc, where h is the Planck's constant, mu prime is the observed frequency, tau is the measure of the uncertainty in the instant at which the photon is emitted, m is the mass of the atom, and c is the velocity of light. This is due to the fact that at this instant, the momentum of the atom decreases by h mu by c, and its velocity decreases by h mu by mc, where h is the Planck's constant, mu is the frequency of the photon emitted, and c is the velocity of light, while m is the mass of the atom. Thus, the position uncertainty arises due to finiteness of tau. What that means is that because there is an uncertainty in measuring the exact instant of time at which the photon was emitted, therefore, we cannot exactly determine the position of the particle. Thus, the fact that tau is finite, we do not therefore know when the velocity changed, and therefore where the atom at a later time is. The uncertainty in momentum is obtained from the equations given above. That is, delta px is equal to m delta v, which is equivalent to mc delta v by v, and this is equivalent to mc v by mc by v tau. We are using here the non-relativistic approximation, that is, v by c is much less than 1. In the above equation, m is the mass of the atom, delta v is the uncertainty in exactly determining the velocity of the atom, and tau is the uncertainty in determining the exact instant at which the photon was emitted. Thus, we have that v is approximately equal to mu and that delta v is approximately equal to 1 by tau, which gives the uncertainty relation delta x delta px is approximately equal to h cross. Now, students, let us look at the role of the uncertainty principle in physical situations, and let us apply the uncertainty principle to such situations and see what is the consequence. So, let us start with the study of the implications of the uncertainty principle in the case of hydrogen atom. Suppose the spread delta x in the position of the electron in hydrogen atom is of the order of its radius. Experimentally, the size of the hydrogen atom is determined to be of the order of around 1 angstrom. Thus, the uncertainty delta x in the position of the electron must be of the order of 1 angstrom or 10 to the power minus 10 meters. Using the first inequality that we have defined earlier in terms of the uncertainty in position and the uncertainty in momentum, we would then imply the uncertainty in the momentum to be delta p is greater than or equal to 10 to the power 10 h cross, where h cross is h by 2 pi and h is the Planck's constant. Since the mass of the electron is approximately 10 to the power minus 30 kg, the uncertainty in the value of the velocity of the electron comes out to be greater than or equal to 10 to the power 6 meters per second. This turns out to be much higher than the known value. It is thus evident that the electron in the hydrogen atom cannot be described even approximately in classical terms, and it makes no sense to talk of a well-defined trajectory of an electron orbit. Implications in Stern-Gerlach experiment. Here, a beam of silver atoms emerges from an oven which contains silver vapor at a temperature 1200 Kelvin. The beam is collimated by passing through a small aperture. Let us see how far the spot on the screen can be localized by narrowing the aperture in accordance with the uncertainty principle. By setting up this experiment, we are again trying to look at the uncertainty principle through the Stern-Gerlach experiment and see at how the finite width of the aperture of the oven is causing an uncertainty in the exact determination of the position of the spot on the screen, and also in the process it is causing an uncertainty in the determination of the momentum. So let us look at this figure and see how we are going to set up the experiment. We have an oven which has an aperture A, and the silver atoms emerge from this oven as silver vapor and move along the positive x-axis towards the screen D. The length between the oven and the screen D is L. The width of the oven aperture is A, and the screen is along the y-axis. Alpha is the half angle that is subtended by the beam of silver vapor atoms on the screen. Now suppose atoms have a component of momentum px along the x-axis, that is, along the direction of the beam. According to equipartition of energy, px squared by 2m is equal to half kT. That means that the kinetic energy of the beam of atoms, silver vapor atoms, is given by this relation, where px is the momentum along the x direction, m is the mass of the silver atoms, k is the Boltzmann constant, and T is the temperature, and half kBT gives the average energy according to the equipartition theorem. From this relation, the value of the momentum along the x direction, that is px, comes out to be px is equal to under root of mkt. Now, the y-coordinate of the atom as it enters the aperture can be determined to a precision delta y is equal to a, where a is the diameter of the aperture. Therefore, an uncertainty delta py in the corresponding component of the momentum such that delta py is approximately equal to h by a, where h is the Planck's constant and a is the width of the aperture. This leads to a spread of the beam with an angle alpha, where tan alpha is equal to delta py by 2 upon px, where alpha is the half angle subtended by the beam on the screen, and delta py is the uncertainty in the y direction or the y component of the momentum, while px is the x component of the momentum of the silver vapor atoms. Thus, tan alpha is equal to h by 2a into under root mkt. This expression is derived by using the relation for delta py and px. In this relation, h is the Planck's constant, a is the width of the aperture of the oven, m is the mass of the silver vapor atoms, k is the Boltzmann constant, and T is the temperature. The spot of diameter d on the screen, which is at distance L from the oven, is given by d is equal to a plus 2L tan alpha, which is equal to a plus L into h upon a into under root mkt. Thus, the minimum value of d of the spot is obtained by differentiating this expression with respect to a. That means that this diameter d of the spread of the vapor silver vapor atoms on the screen with respect to A. When we differentiate that, then we get A square is equal to LH upon 2 into under root mkt. From this expression, if we substitute the value of A, we get D minimum is equal to 3 by under root 2 into under root L into H upon within brackets mkt to the power 1 by 4. Here the D minimum is obtained because when we differentiated the value of D from the above equation and equated it to 0, we could get the value of the width of the aperture, and then using that value of the width of the aperture, we substituted that back into the relation for D and we got the minimum value for D. Since the right hand side of this expression, that is the expression for D minimum, has all fixed constants, it is clear that one cannot minimize the spot on the screen beyond a certain value. Thus, in this manner, because of the finite width of the aperture of the oven, there is an uncertainty which gets introduced in the y component of the momentum as well as in the exact determination of the spot of the atoms that is hitting the screen. And this uncertainty in the exact determination of the spot is given by D minimum. Estimating rest mass of exchanged quanta using uncertainty principle in fundamental interactions. The origin of fundamental forces of nature taking place between different constituents is believed to be due to the exchange of the quanta. One can make use of the uncertainty principle, that is, delta E delta T is approximately equal to H cross, or the uncertainty in determination of the energy and the uncertainty in the determination of the exact time is approximately equal to H cross, where H cross is H by 2 pi and H is the Planck's constant. Now, to estimate the rest mass of the exchanged quanta for the range of interaction, we need to see that the range of interaction is related with the energy E of the field quantum exchanged. The exchanged quantum, being virtual, exists only for a short time t less than equal to h by E, assuming that the field quanta travel with the velocity of light. And this is because for light, the field quanta is an electromagnetic radiation, and all electromagnetic radiation, including light, will travel with the speed of light, that is c. So, we can find out the range. Now, if the field quantum has a rest mass m, it must have at least an energy which is given by E is equal to mc square, where m is the rest mass, c is the velocity of light. Therefore, r0, that is the coordinate which is related to time in the 4 vector space, where r1, r2 and r3 are the x, y and z coordinates, and r0 gives the time coordinate. So here r0 is equal to ct is approximately equal to hc by E, where c is the speed of light, t is the time coordinate, h is the Planck's constant, and E is the energy as given by the above relation. Thus, range is inversely proportional to mass. In gravitational and electromagnetic interactions, range is infinite. That means that the effect of the gravitational or the electromagnetic field is infinite. and thus the rest mass of the particle is 0, which means that R0 is approximately equal to h by mc, or m is approximately equal to h by R0c. So, as discussed above, in the case of gravitational and electromagnetic radiations, since R0, the range of the interaction is infinite, therefore the rest mass of the particle goes to 0, and that is why photons have 0 rest mass. Complementary principle by Bohr. Now let us revisit the Young's double slit experiment in the context of the uncertainty principle, and let us probe the question: can we say that the photon or electron which reaches some point of the interference pattern has followed a definite trajectory, passing through a particular one of the two slits? The probability interpretation says no, which means that it says that it is impossible to exactly determine through which of the two slits the photon actually went. And if we try to determine this accurately, we might lose the interference pattern that we obtain. So, in order to see whether this is actually true or not, let us analyze this question in a different way. Let us now suppose that the trajectory is a moving wave packet with lateral extension less than half the separation A between the two slits. By doing this, we are trying to ensure that the wave packet can go through any one of the two slits. Now, by doing this, or rather by imposing this condition, what we need to check is whether there will be an interference pattern or not. The reason for this is that since now, in order to make the wave packet move like a particle, we have tried to reduce the size of the wave packet, or the lateral extension of the wave packet. So, we need to see whether such a restriction is going to affect the interference pattern or not. So, now let us look at the analysis further. Based on the uncertainty principle, we see that the angle theta giving the direction of motion of the particle is uncertain by an amount. Theta is approximately equal to tan theta, which is equal to delta py by p, which is equal to 2h by pa, and this is equal to 2 lambda by a, where delta py is the uncertainty in the exact determination of the y component of the momentum, p is the momentum, h is the Planck's constant, a is the separation between the two slits, or the half separation between the two slits, and lambda is the wavelength of the wave that is traveling, which is associated with the particle. Now, since the angular separation between successive maxima of the interference pattern in Young's double slit is lambda by a, where lambda is the wavelength of the wave packet or the wave associated with the particle, and a is the half separation between the two slits. Since the above uncertainty clearly exceeds this limit, which means that the uncertainty that was given by the angle theta, which was equivalent to 2 lambda by a, is greater than the angular separation of the Young's double slit, which is given by lambda by a. Therefore, what we see is that the interference pattern is completely washed out, which means that when we try to make the wave packet very compact so that it behaves like a particle, that means that when we try to restrict the extension of the wave packet to such an extent that it starts looking like a particle, what is happening is that it then loses its ability to display the wave properties. As a result, what happens that the particle and the wave aspect of a physical entity cannot simultaneously be executed, or that it is impossible to simultaneously view both the wave as well as the particle aspect of a particle. And this is what the Bohr's complementary principle is, stated as the particle and the wave aspect of a physical entity are complementary and cannot be demonstrated at the same time. Now, students, let us summarize what we have learned in this module. Firstly, we came to know the statement of Heisenberg's uncertainty principle for all the three conjugate coordinates, that is, position and momentum, angular momentum and angular displacement, and energy and time. Then we got to learn through a measurement experiment how the process of trying to determine the position precisely using a precise value of momentum not only gives an inaccurate position determination, but at the same time also introduces the uncertainty into the momentum measurement. Then we got to learn through another measurement experiment that even if the position initially is known exactly and precisely, the process of measuring the momentum not only gives uncertainty in the momentum measurement, but at the same time introduces uncertainty in its position measurement. Then we got to know through a few typical examples the implications and consequences of using the uncertainty principle and how it affects those examples. Then we also learned about what the complementary principle given by Bohr is. Thank you.